Hello everyone, myself Dr. Sharmila Pandey, Associate Professor of Chemistry in the School of Sciences, Sage University, Bhopal. Today I will discuss on the topic Orgel diagram. So Orgel diagram we get basically from the splitting of terms. Terms means energy states, and this splitting of terms happens in crystal field, that is in presence of octahedral or tetrahedral field. So what is terms? Energy levels of atoms or ions that arise due to inter-electronic repulsions. And the term symbol we represent as 2s plus 1 Lj. 2s plus 1 is the spin multiplicity, L is the orbital angular momentum, and J is the overall angular momentum quantum number. These terms again split in presence of octahedral and tetrahedral ligand field. So generally these terms split in SPDF. SPDF. In these four terms they splits. So generally S term is non-degenerate, so there is no splitting. P term does not split but becomes a triply degenerate T1G term. D term has a five-fold orbital degeneracy and it splits in EG, which is doubly degenerate, and T2G, which is triply degenerate. F term has a seven-fold orbital degeneracy, A2G plus T1G plus T2G. A2G is a singlet state and T1G, T2G, these both are in they are triply degenerate. So from this table we can see S for S term number of states, that is 12 plus 1 is 1, and the component in an octahedral field is a 1G. For P, degeneracy is 3, components T1G. For D term, the degeneracy 5, components T2G plus EG, and so on. We get the components in an octahedral field for FGHI also. And similar splitting occur in a tetrahedral field, but the G level are no longer applicable there. So Orgel diagrams are basically correlation diagrams, which show the relative energies of the electronic term in transition metal complexes. Creator is Leslie Orgel. Orgel diagrams are restricted to weak field ligands, that is high spin complexes. Because Orgel diagrams are qualitative, no energy calculations can be performed from these diagrams. In an Orgel diagram, the parent term are written in the middle of the diagram, in the center of the diagram, like 2D. For D1 case, it is 2D. Then we show the splitting, like we have learned, D will split in T2G and EG. So to these two type of splitting will be shown, and here we have to write the spin multiplicity as 2, then the symbol as 2T2G, and the upper one will be 2EG. So this is how we present Orgel diagram. Now we will see what will be the Orgel diagram for D1 to D9 octahedral and tetrahedral complexes. For Orgel diagram in D1 system in octahedral field, the d orbital splits into T2G and EG set of orbitals. For the D1 ion whose term symbol is 2D, there are therefore two possible electronic configurations. So we can see the one electron, when it is in the ground state, it will be T2G1, and in the excited state, it will be EG1. Now in the ground state, we can see there are three possibilities. The electron can stay in this orbital, that is dxz or dyz or dxy orbital. So three possibilities are there. So we know that term 2D splits in T2G and EG. But what will be the ground term? So looking at the possibility of arrangements in the ground term, we can say that as three possible arrangements are possible in the ground term, so T2G will be the ground term. So T2G will be the ground state term. What will be the excited state? In the excited state, the electron, unpaired electron can be in the dz square or in the dx square minus y square. So we can see two possible arrangements, and that is why this E, which is W degenerate, will be the excited term. So in case of D1 system, it is 2D and the ground term will be 2T2G, excited term will be 2EG. So here, from here, actually why it is important, from this diagram we can say only one electronic transition is possible from 2T2G state to 2EG state, and that is why we get one broad spectrum in case of any D1 metal ion like titanium plus 3. If we think the case of D2 system, D2 metal Ml value is +2, +1, 0, -1, -2. So D2 system 2s plus 1 equals to 3. It is triplet state. L equals to 3. So the term will be F. So the term symbol will be actually 3F. Now the 2 electron can be in the ground state at T2G to EG0. So the 2 electrons can stay in these 2 orbitals or these 2 orbitals or these 2 orbitals. So again we can see there are 3 possibilities of these 2 electrons in the ground term. Okay, so in the excited state, we can see T2G1, EG1. Again, this one electron can stay in these 3 orbital in 3 possible way, and the one electron at the EG orbital can stay in 2 different, only in 2 possible arrangements. So the multiplicity will be 2 into 3 equals to 6. So 2 into T subcomponent terms. So between these 2 T terms, one is associated with a free ion triplet P term. So when this is the free ion, we have determined that the ground term will be 3F. But in the closed energy, there will be another state, another term which will be 3P. As both have same spin multiplicity, so the electronic transition is possible from 3F to 3P. So the between these 2 T subcomponent terms, one is associated with this 3P term. Now in the second excited state, when both the electron is are in the EG state, so 2 electron in 2 orbitals. And how many possible way we can arrange them? Only one possible way arrangement is there. So the orbital multiplicity is 1. So we know that F term has 7-fold degeneracy, and for D2 the term symbol 3F, the splitting will be A2G, T1G and T2G. But as we have seen that in the ground term, when T2G 2 electronic configuration is there, so there are 3 possible arrangements. The orbital multiplicity was 3 into 1 equals to 3, so T subcomponent term. So now we know among these A2G, T1G, T2G, the T term will be the ground term. So 3T1G is the ground term. Next will be 3T2G. From here we are getting that 2 T subcomponent sum. So the first excited state, T1, EG1. So we are getting this 3T2G. Along with this, it is associated with another term associated with 3P, so 3T1G. And the second excited state where the electronic configuration is T2G0, so the term 3A2G is associated with that. So 3A2G will be the excited state. So in the 3F term, the 3 terms will split like 3T1G is the ground term, and the next 2 term will be 3T2G, F and 3A2G. There will be another term associated with 3P ground term, which is 3T1G P. So for in case of D3 system, here we can see ground state, only one possible arrangement, because all the 3 orbitals are having 1 electron each. So the ground state will only one possible arrangement possible. In the excited state, we can see 3 possible arrangement in the T2G state and two possible arrangement in the EG state. So total possibility 2 into 3 equals to 6. So T2G and T1G, they will be associated with the excited state. And as only one possible arrangement was there in the ground state, so A2G will be the ground term. So here we can say 4A2G is the ground term, then comes 4T2G and 4T1G. Here also, because of the close association, closer in energy, 4F and 4P in the free ion term, another term as for 4T1GP will be there, whose energy are closer. So in addition to the two triplet excited state 4T2G and 4T1G arrived from F term, there is one more excited state 4P, which splits into 4T1G. In case of D4 system, again it is similar like the D1 system, but we can see, so if I have D terms and it will split in two terms, EG and T2G. Now we have seen in case of D1 that T2G was the ground term and EG was the excited term. Reverse will happen in case of D4 system, because in this case we can see at the ground state there is two possible arrangement of this electron at the EG state, right? So the total possible arrangement is 2. That is why the EG will be the ground term, and in the excited state these two electrons can be arranged in the T2G state in 3 possible ways. So 5T2G will be the excited term. Now if we see the D5 and D10 case, we can see for a D5 ion ground term is 6s. For D10 ion the ground term is 1s, and we have already seen s term is non-degenerate, so no splitting. So 6s term will not split, it will give rise to the term 6a1G. Now we can calculate these, we can determine the ground term and excited term from D1 to D9 all the systems. So for D6 system, we can see that the ground term is 5D, and here from here we can see one downspin electron can be in 3 possible arrangement in the T2G set. So 5T2G will be the ground term. How they can stay? The downspin can be in this DXZ or DYZ or DXY. So 3 possible arrangements in the ground state. So T2G is the ground state and EG will be the excited state. Similarly, D7 and D8, as we have seen, the ground term is 4F for D7 and 3F for D8. So they will split in 3 terms, T1G, T2G and A2G, and there will be another free ion term 3P will be in will give rise to another term T1G. Now we can see in case of D7 system where the term symbol is 4F, 3 possible arrangements in the ground state are possible. So if we draw the D7 system, we will see 3 possible arrangements are possible in the ground state. So in this case, T2G is the ground state. But if we go to the D8 case, we will see that if ground term with spin multiplicity 3, the term symbol is 3F, only one possible arrangement in the ground state, and so A2G will be the ground state in case of D8 system. In case of D9 system, D9 ion, the term symbol is 2D. So D term has a 5-fold degeneracy EG and T2G. If we go in the similar way, we will see T2G6 for the D9 ion, there are 2 possible configuration, T2G6 EG3 or T2G5 EG4, and these gives rise to the 2 EG and 2 T2G terms. And 2 EG will be the ground term and the excited term will be 2 T2G. Orgel diagram for D9 ion in the octahedral and tetrahedral field, if we will see for tetrahedral, it will be the ground state will be 2T and the excited state will be 2E, which is exactly reverse as the uh, let us first discuss the D9 octahedral case. In this case, we can see octahedral, two possible arrangements are there in case of ground term. So 2E will be the 2EG will be the ground term, 2T2G will be the excited term, but reverse happens in case of tetrahedral. In case of tetrahedral, three possible arrangements possible in the ground state. So 2T is the ground state, and in excited state 2 possible arrangements are there. So it will be 2E will be the excited state. The tetrahedral D1 and octahedral D9 have the similar Orgel diagram. So from that we can say, or if the octahedral D1 will be equal like D9, D2 will be like tetrahedral D8, and so on. The octahedral D9 will be equally similar as D1 tetrahedral system. So actually Orgel diagram of high spin D1 to D9 metal ions, we can represent them in two types of Orgel diagrams. One where EG and T2G splitting will be there. In some case, doublet E is the ground state and T is the excited state. Other cases, T is the ground state, E is the excited state. Depending on tetrahedral and octahedral, we use G. And the other type of case where F is the ground term, these kind of splitting are there, where three splitting are there from both the tetrahedral or octahedral case, and another term arises from the another free ion term T1P. So by these two ways, we can represent the Orgel diagram for all high spin D1, D9 octahedral as well as tetrahedral metal ions. Thank you.